Hello friends, welcome back to this online certification course on watershed hydrology. I am Rajendra Singh, professor in the Department of Agriculture and Food Engineering at Indian Institute of Technology, Kharagpur. We are in module 3, this is lecture 3 and we will continue with stream flow measurement. This is part 2 of stream flow measurement. In this lecture, we will continue with area velocity method which we started in the previous lecture. Then we will go to dilution technique, we will talk about electromagnetic method of stream flow measurement, ultrasonic method of stream flow measurement, and we will also talk about acoustic Doppler current profiler ADCP. Now, if you remember in the previous lecture, we discussed about the velocity measurement and we said that it is a current meter typically which is used as an equipment for measuring velocity, and we also discussed that if it is a vertical profile, then typically the velocity distribution is something like this, and that is why, because velocity distribution in vertical profile is not uniform. So, we either use 6-10 rule, that is we measure velocity at 0.6 d from measured from top, and or we make two measurements at 0.2 d and 0.8 d and take average of that. That is, since flow velocity is typically measured at 0.6 d or 0.2 d and 8 d from the surface, the depth d of the stream must be known. So, obviously, we have to have fair idea about the depth at which we are making the measurement. So, when the stream depth is small, the depth at various locations may be measured by sounding rods or sounding weights. So, we can use a rod or a weight to immerse. If it is a weight, then we cable with a cable we immerse and then measure the depth. It is very similar to staff or wire gauge which discussed in the previous lecture for measuring the stage. Only thing is that in stage we measure with reference to certain datum from bottom, where in the case of depth we measure from the water surface to the depth of to the bottom of the channel bed. However, when the stream depth is large or when the results are needed with higher accuracy, then we use an instrument called echo depth recorder. And of course, as the name itself suggests, it is a sound based device. So, this device transmits a sound pulsage into the water by a transducer and receives the echo reflected from the stream bed, and the time interval between the emission of the sound pulse and its return as an echo is used to estimate the depth of water. So, this is a typical, you see it is a transducer is there and there is a recorder, and obviously the sound waves are sent towards the bed, and when they hit the bed they return, and then both based on the time gap between these two, that is sending and receiving, the depth is estimated, calculated, and of course, the equipment is calibrated in a particular way. Then of course, in the area velocity method, the another important aspect is the cross section of the. So, we have to have a fair cross section idea about the cross section, and also where are we going to make the measurement of the velocity, where are we going to make the measurement of the depth. So, all these things are very important. So, typically we use a method called midsection method, and what happens in that, in this midsection method, the river cross section is divided into n-1 vertical segments. So, here you can see that at depth W1, W1, W2, so on, we have divided the entire cross section into n-1 segments, and the stream flow is calculated using the following equation. It is nothing but sum of the discharges in individual segments. So, if we are able to estimate in all discharge in all the n-1 segments, the sum of that will give us the total stream discharge. And basically for there are, as you can see that there are two end segments and then there are other segments in the intermediate between these two end segments. So, for I n to n minus 2, that is n2 to n minus 2, we use this formula that delta qi, that is discharge in the ith segment, is depth of ith segment times half width to the left plus half width to the right into velocity at ith vertical. So, it is yi plus wi by 2 plus wi plus 1 by 2 plus vi by 2. So, what is happening here is you can see that we are dividing the segment and then we are marking the mid of that for measuring the depth and also for measuring the velocity. Depending upon the depth, we will measure the velocity at 0.2 y is the depth here. So, at 0.2 y or 0.2 y and 0.8 y or 0.6 y, and that velocity, that is the average velocity, will use for that particular segments. So, here basically it is nothing but the trapezoid equation which we are using, half width to the left, half width to the right, and velocity at ith. So, for example, if you consider this particular segment, then of course, this is yi is here, and of course, the half width of wi and wi plus a half width on either side is taken into account for finding out the cross sectional area multiplied by the depth which is measured, which is yi in this particular thing. So, for all intermediate segments, that is starting from I equals to 2 to I n minus 2, we use this formula which is shown here. In the case of end segments, that is for the first and last sections or segments, they are taken to have triangular areas and then area is calculated accordingly. So, if you consider area of first segment, then it is nothing but area of triangle ACD, which is here. You can see that it is here. This, if you consider, this is W1 bar, so this is W1 bar, and this is your Y1 here. So, if we this is the triangular area we are considering, that is shaded pink here. So, that is what is represented here. So, ACD, which is half into W1 bar, that is half into width into depth. Depth is h. So, half, and W1 bar is W1 plus W2 by 2, as you can see from here, it is W1 plus W2 by 2. So, half of that. So, that is, so W1 bar is W1 plus W2 by 2 basically. And h, for calculating h, because in the formula we have to find out h, which is here. So, for that we use the similar triangle theory, that is, we consider that triangles ABF and triangle ACD, they are similar triangles, and therefore, W1 by Y1, that is this side by this side of ABF, is same as this side by this side of, that is AC by CD for triangle ACD, and we are interested in finding out CD, which is h. So, from here W1 by Y1 is W1 plus W2 plus 2 by h, and that will give us the value of h, and if we substitute this value of h in this equation, which is here, that is, then the area of first segment will be, finally we will getting in this form, that is W1 plus W2 by 2 square by 2 W1 into Y1, which is just the manipulation of this entire multiplication terms here. So, this is how we will get the area of first segment, and in a similar fashion, because the last segment, that is this segment, if we consider this end segment, this is also taken to have a triangular area, and then the area of this particular segment, that is delta A n minus 1, will also be found out and in similar fashion using the similarity theory, and here it will come out to be W n plus W n minus 1 by 2 square by 2 W n times Y n minus 1. So, this is Y n minus 1, that is where we are measuring Y n minus 1. So, discharge of first segment will be delta A 1 times V I bar, which is the average velocity in the first segment, and then discharge of last segment will be delta Q n minus 1 will be area times average velocity in that particular segment. So, the total then obviously we know, because we have calculated earlier the discharges in all other segments. So, sum of all these will give us the total discharge by the midsection method. And let us take an example here. The following data are obtained from the current meter gauging of a stream. Compute the stream discharge. Rating equation of current meter is V equals to 0.4 n plus 0.08, where n is revolution per second and V is the velocity per meter per second. And as you can see here, the data distance from one end of the water surface, the distances are given across the stream, and at different depths are mentioned here, and then current meter data like depth and number of revolutions, what depth or how many revolutions are there, in what time, that is recorded here. So, as you can, if you notice here, at smaller depths there is just a single measurement, but when the depth is more, there are two measurements, that is 0.2 plus and 0.8 d measurements are there here also you can see. So, this has to be taken into account while finding out the discharge. So, here this is the raw data which we just now saw, and we know that velocity is 0.4 n plus 0.08, which is the equation given. So, obviously, we have to find out the value of n, since revolution and time is given. So, we can find out the value of n here, and once we know the value of n, we can put the value here and we can find the velocity at different depths or distances and different depths where the velocity, the current meter readings have been taken. So, these are all here. So, of course, in sections or at depths where only single measurement is done, there the velocity is directly we get, but in other cases, for here for example, we have to take the average of these two to get the average velocity. So, average velocity in this particular section is 0.31 and so on. So, 0.334, 0.352 and so on. So, that is the sectional velocity value we have obtained for different sections. Now, once we have got the sectional velocity, the next thing is, of course, because if you remember in the formula, the width also is taken into account. So, W1, W2, Wn n minus 1 comes into picture. So, that is why we have to get the width, and of course, we know the distances. So, we know the segment width we can find out, and it is all throughout it is 2 meters. So, segments are all of 2 meters we know already from the data. So, if we have to find out the discharges in section 2 to section n minus 2, that is from I equal to 2 to n minus 2, then obviously we know this is a formula we have to use. So, for example, if you consider section 2 here, then obviously delta Q2 is Y2 times W2 by 2 plus W3 by 2 into V2, and here the depth is for section this depth is 2.6, which is here Y2. W1 and W2 and W3, they are same values. So, it does not matter because W2, W3, W1 all are 2, and of course, here we have to take the average velocity which we calculated earlier for this section, that is 0.31. So, putting that, we get the discharge for this particular section is 1.612. So, similarly, we will calculate the discharges for all intermediate sections, that is Q3, Q4, Q5 and Q6 for different sections, and these are the values we get. So, this is for intermediate sections, and for first and last section we know that we have to change the formula, and that is here W1 plus W2 by 2 square by 2 W1 times Y1 times V1 for first section. So, all W's are 2. So, that is not a problem putting those values, and Y1 is depth is 1 for section 1. So, it is 1, and velocity we found out is 0.18. So, 0.18. So, for using that we get the discharges 0.405. Similarly, for the last section we get the discharges 0.863. So, these are the discharges at different segments, and of course, as we know that the sum of discharges will be the total discharge. So, which comes out to be 17.535 cubic meter per second. So, that means the total stream discharge for the given data is 17.454 cubic meter per second. Then we move to the next method, that is dilution method or dilution technique, which is also known as the chemical method. And this particular method is useful for small streams and streams with lots of boulders, wood and other roughness elements. So, a lot of obstructions are there where a current meter probably will not be able to work. So, that is why we use this chemical method. And this method or dilution technique works on the principle of continuity, and the principle is applied to a tracer which is allowed to mix completely with the flow. So, a tracer is put into the stream and it is allowed to mix, and of course, then we measure the concentration and then use the continuity principle to find out the stream flow or the discharge. Of course, there are some limitations on the size of stream to be measured, that is, it cannot be used, this particular technique cannot be used if the stream is too wide, because there could be currents and then the tracer mixing may not be uniform. So, we may not get the accurate data. And there are two methods which are followed in dilution technique. One is the constant rate injection method, or which is also called as plateau gauging, and sudden injection method, slug injection method or integration method. These are the names which are used. Slug injection is a very common. So, constant rate injection and slug injection, these are the common terms, and they basically they refer to the rate at which or the method by with which we inject the tracer into the stream. So, we will see these methods. Before that, there are three main types of tracers which are used. The first one is the chemicals like sodium chloride, the common salt which we use at our home, or say sodium dichromate, that can be used as a tracer. Of course, in that case we have to use a electrical conductivity meter, because if you put salt into water, the electrical conductivity changes. So, that conductivity is measured in this case. And then we can also use radioactive materials like bromine 82, sodium 24 or iodine 132, or we can also use fluorescent dyes, that is rhodamine WT, where WT stands for water tracer, rhodamine water tracer, or sulforhodamine. So, then of course, as you can say they are fluorescent, so we can get different colors also, like red color, green color and so on and so forth. Now, the first one is the constant injection method. Coming to methods of injecting, the first one is constant injection method, and we already know that the entire procedure is based on the continuity principle. So, what happens here is that the tracer with a known concentration C1 is injected at a known flow rate Q1 into a stream at section 1. So, if this is our section 1, then what happens that here we known concentration tracer we pour into water at a constant rate. So, rate also we know the concentration and we know the rate at which we are putting the tracer into the stream. Then stream concentration C2 is measured after complete mixing at section 2, which is a little bit away. And of course, this plateau is method also is called, because once the complete mixing is there, then it is expected that the tracer concentration will become constant. So, it will be a horizontal line or a plateau will be obtained. So, that is why we measured C2 from a background value of C0 at time t1. So, initially before experimentation, we also measure the concentration, which is, let us say, C0. So, after that we know C1, C2, C0 and Q1. Knowing all those, we use the continuity equation, and discharge is obtained like Q1 C1 plus Q2 C0 is equal to Q2 plus Q1 C2. That is like we know the flow is taking place with certain discharge here with the background concentration, and this is what we have poured at known discharge. And of course, when we are measuring, it is Q2 plus Q1, that is the both sum of two discharges plus Q2, and using that we can find out. So, we know Q1, we know C1, C2 and C0, so we can find out what is the discharge. So, this is the constant injection method. The other method is slug injection. So, in this case a known mass of tracer is dumped into the stream. So, here we depend on the mass, not on the rate. So, we dump the known mass into the stream, and then the whole peak is measured after mixing downstream. So, we measure the entire peak, like where from it has started, gone up, and then of course, it will fall down to same value. And then discharge is calculated by using the relationship that Q equals to mass, with which the known mass which we have dumped, divided by the area under the curve, and using that we find out the discharge. Let us take a very simple example. A 25 grams per liter solution of a fluorescent tracer was discharged into a stream at a constant rate of 0.0001 cubic meter per second. The background concentration of the dye in the stream water was found to be 0. At the downstream section, sufficiently far away, the dye was found to reach an equilibrium concentrate of 5 parts per billion. Estimate the stream discharge. So, here we know it's the tracer is being injected at a constant rate. So, obviously, it is a constant injection method. So, that means we have to use this formula. So, the values which we know is Q1, that is the rate at which the tracer is being injected, and then concentration C0, the background concentration is 0. This is the known concentration of the tracer, that is 25 grams per liter or 0.025 kg per liter, and C2 is 5 ppb parts per billion, and we know 1 parts per billion is 10 to the power minus 3 megagrams per liter. So, that is why we are writing it is 5 into 10 to the power minus 9 kg per liter. So, because Q1, C1, C2, C0 are known, if we put all the known values here, we get Q2 equals to 50 cubic meter per second. That means, with the tracer method, the discharge in the stream is 50 cubic meters per second or 50 cubic. Then we go to the third method, that is electromagnetic method, and electromagnetic method of stream flow measurement utilizes electromagnetic sensors to estimate the velocity of water within the river or stream, from which the discharge or flow rate can be calculated. So, important thing to note here is that the electromagnetic sensors which we use, they measure the velocity. So, that means, finally, it is the area velocity method it is used here, but instead of using midsection method, in this case the area is taken into account while developing the relationship itself, which we will see. Now, as far as principle goes, this method is based on Faraday's law of electromagnetic induction, and according to this law, the motion of water flowing in a river cuts the vertical component of the Earth's magnetic field, and electromotive force or EMF is induced in the water. This EMF can be sensed by electrodes or probes on each side of the river, and is found to be directly proportional to the average velocity of flow in the cross section. So, as you can see, we have to have a certain setup, that is, we have to have cables, we have to have probes installed on either side, and of course, we have to have instruments to measure all those signals. So all those arrangements have to be made, as is being shown here. Now, since the Earth's magnetic field may be impacted by the electric power lines which might be crossing the river or stream where this method is being used, or any other electrical devices that are operating nearby, typically a vertical magnetic field is generated by means of a coil buried in the river bed or over it, through which an electrical current is driven. So, basically it is a little bit more complicated, becomes little more complicated because we may have to take the cable buried inside the stream bed, or we have to put a arrangement so that this cable is just moving over the or in place just over the water surface. And the potential generated is proportional to the width of the river multiplied by the magnetic field multiplied by the average velocity of flow. And for a system with the coil buried in the river bed, the discharge can be found out using this relationship, where E dash is the electrode potential, that is the voltage that is changed we are measuring by the probes. H is the depth of flow, that is means we have to measure the depth also while making this measurement, or we have to know the depth. I is the coil current, so that's current we are sending it in amperes, and K and N are system constants. So, K and N are system constants. So, that is why I said that though it basically measures velocity, but through system constants area is also taken into account. So, discharge equation is obtained by the velocity area principle, in which the velocity is inferred from the electrode potential, that is what we have shown here, and it is multiplied by the cross sectional area of flow. The depth of flow appears in the equation. So, you can see here the depth of flow h is already being used in the equation, but the channel width is accounted for in the design of the coil, which extends the full width of the channel and in the empirical calibration. So, because the cable is put below the bed, so automatically the stream width is taken into account by the coil design as well as while calibrating. So, this K and N, which are constants, they take care of the width basically. Then comes there are certain advantages of this methods, like for example, this is non-intrusive method. So, this electromagnetic method is non-intrusive and does not require physical contact with the water, reducing the risk of disturbance to the stream bed or aquatic habitat. So, other methods we have seen that either we took either you put a staff or a wire gauge or for measuring the depth or stage, or even if you use the current meter for measuring the velocity, then always there is a risk of disturbance to the stream and of course, the aquatic habitat, but that is not the case in this method. Adaptability, it may be used to measure stream flow in VD rivers and rivers with silty or moving beds. So, obviously, even if the cross section is not an issue here, because directly we are not taking into account, width is being taken into account while designing the coil or while calibrating the instrument. And there is a continuous monitoring is possible, because all other methods we have to carry out the experiment, that means time, I mean you have to make the arrangements, but here once the setup is installed, then you can have the continuous monitoring of stream flow, and obviously it can provide valuable data for hydrological studies. However, due to cost considerations, the method is used for rivers having a maximum width of 30 meter, and limit is mainly set by the need to insulate the channel with the membrane. So, obviously, the cable which we take, that has to be insulated, or the entire channel has to be insulated, so that there is no danger of current causing any damage to human being. So, that is why this it becomes a costly affair. Then comes the ultrasonic method, which of course, ultrasonic means it is a sound based. So, ultrasonic river gauging is based on the continuous measurement of stream velocity at chosen depths by recording the difference in time for sound pulses sent obliquely across the river in opposite direction. So, here you can see the transducers are there, and the sound waves are sent not in straight channel width, but in an oblique at certain angle, and the transducers are mounted on each bank of the river to transmit and receive these sound pulses. So, as you can see here, there are two transducers are installed. We calling it upstream, downstream, because of the direction in which or the angle which is being made. The angle between the transducer line or flight path and the direction of river flow is normally kept between 45 degree and 60 degrees. So, that is talking about this theta. This theta will be normally limited between 45 and 60 degrees. Simultaneously, the average depth of flow is measured using a float recorder or equivalent instrument. So, obviously, we also measure the depth of flow. Discharge is then calculated by velocity area method from the mean velocity component along the flight path, the average depth of flow, and the channel width. So, that means these transducers or this ultrasonic method also gives us velocity, and then we have to use the area velocity method for finding out the discharge. And this is the equation which may be used for determining the discharge, where L is the path length. So, here these are two transducers. So, the distance between them is path length in meters. VL is the stream velocity, that is in the direction of flow. BP is the component of the stream velocity along the acoustic path, which is being used here in calculating this T bar here. And C is the velocity of sound in the water, which is taken approximately 1500 meter per second, which is also used here in calculating this T bar. Theta is the angle with acoustic path makes with the direction of flow, that we already discussed. And TAB and TBA are travel times from A to B and B to A. So, we are calculating TAB and TBA, and the difference is giving us delta T, and T bar we are being calculating, and D bar is average depth of flow along AB. So, D bar is average depth of flow along AB. So, depth is being taken into account, width in terms of the path length is being taken into account, and of course, the velocity. So, that is how we can find out the discharge using this method. And this method is applicable to rivers up to about 300 meter in width. Up to that, it is found that sound waves are not disturbed and it gives a good reading. And there is no, it is used where there is no stable stage discharge relationship and a major structure is unsuitable or not feasible. That means where the cross section is not very stable, where we cannot install a measuring structure, or where we cannot develop a good stage discharge relationship or rating curve, there this method is suitable. And it method is also appropriate under conditions of backwater from dams, tides or other causes. So, if the section where we are interested is pretty close to a dam or pretty close to the sea, where the backwater effect could be there, and there this method works fine. Lastly, we will talk about Acoustic Doppler Current Profiler, ADCP, which is an advanced instrument to measure flow velocity in a large stream or water body. And this also has a transducer assembly consisting of 4 transducers, each pointing between 20 and 30 degrees from the vertical. So, as you can see here, this is the transducer assembly. There are 4 transducers, and of course, they make an angle of 20 degree to 30 degree, as already mentioned, from the vertical. And they send sound signals or sound waves and the Doppler effect to measure 3D velocity. So, of course, the sound pulse is transmitted, and of course, it is also received. Once it hits the sediment particles or the bed, it returns, and that is measured. It measures the velocity of the entire vertical profile at once, not just at a point like current meter. So, that is the advantage, or that is the advancement here, because you remember that if we use the current meter, then we get a velocity only at single point, but with ADCP we get the measurement for the entire profile. Typically, we use a boat or a river platform for carrying out the bathymetric survey in a stream or in a water body. And this bathymetric survey produces depth and velocity profiles, as you can see here. Typical profiles we obtained, as you can see here, and it also helps determine the total suspended solids, because sound waves they also hit the sediment particles and return. So, that is also taken into account. And ADCP allows access to even remote sites for velocity and discharge measurement, because it is a very simple instrument which we just have to be immersed for getting the 3-dimensional velocity. So, anywhere you can go with a boat, you can use this instrument. So, with this we come to end of this lecture, and we have seen various methods of measuring stream flow, and we still continue with this because there are some other methods which we need to discuss. Up till now we have been discussing only the direct methods. There are certain indirect methods also we will discuss in the next lecture. Thank you very much. Please give your feedback and also raise your doubts or questions which can be answered on the forum. Thank you very much.